Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is the fourth part of a lecture on functions for intermediate algebra. We've already talked about what a function is, several ways we could represent a function, be that through word problems or graphs or equations or tables. We've talked about function notation and evaluating functions, and now we're going to just talk about graphs of function. In fact, I've already introduced some graphs of functions, specifically interpreting values from graphs and stuff like that, but we'll venture into a little more of that here, as well as talk about intervals of increase and decrease. Now we'll go ahead and start with an example that's more of an application. We have a function. This is a graph of the function capital T of little t. So the inputs are the little t and the outputs are capital T. And this gives the tidal height in Seattle, Washington for October 4th to October 5th, depending upon the hour of day. So the independent variable, or input variable, is the time of day in military time. And the output variable is going to be, or our dependent variable, is going to be the ocean height in feet. And we're going to interpret some things on this graph and talk about what these items mean. And this is a huge skill for any type of intermediate algebra class. Find t of 1630 means that you are going to plug 1630 into your function. In other words, you're going to look along the independent variable axis for the value of 1630. Remember, these are hours, so 1630 is equivalent to 4:30 p.m. So that's 12 p.m. That's 1, 2, this is 2, 3. That'll be 4. So 1630 will be right about here. And if you draw a straight line going up, you see that it meets the curve at a height of, roughly, let me go ahead and connect that up here. Looks to be about almost 8. Just shy of 8, in fact. So let's go ahead and say that's about 7.8 feet. Now notice a few things here. I put in t of 1630 is roughly equal to 7.8. Again, using the power of function notation so that not only when somebody comes in, they can see that I'm saying the input is 1630, but I'm also saying the output for that is 7.8. I'll also list out what that 7.8 is. It's in feet. The interpretation here is that at 4:30 in the afternoon, the tidal height, or the ocean height, is 7.8 feet. Part B is asking for what values of t is the function equal to 6. Some people say, when is the function value equal to 6? When are the outputs equal to 6? When is t equal to 6? They all mean the same thing. So what I'll do to illustrate this is I'll draw a line at the level of 6 here, just so we could see. And then wherever I intersect the graph of our curve here, I'll draw a line straight down. So it looks like I intersect the graph right here. I'll draw a line straight down. And it also looks like I intersect the graph right there. So let's see, this looks to be 11, 10, 9. It's about a little bit past maybe 8:45. So I'm really roughing it here. So it's 8:45. Looks like the first time the tide hits a height of 6. And then later on, let's see, this is 5. Nope, it's not 5. This point right here is midnight, so that's 1 a.m. That's 2 a.m. So this right here is 2, or 0200 hours. So it looks to me, according to this graph so far, it's at 8:45 and at 2. So for what values is of little t, or in other words, what time values, is the tidal height equal to 6? Well, that's t equals, well, maybe I should say roughly equals, because we're actually eyeballing this. 8:45 and t roughly equals 2 a.m. So 2:00. The next question is asking what's the maximum value of our function t, and what's the minimum value of our function t. The maximum will occur at the overall maximum on this curve here, when it reaches the maximum height. That'll occur right here. And it says what is the maximum value. That looks to be about 11. The maximum value is about 11. So the maximum value, roughly 11, and I'll say feet because that's the interpretation. The minimum will occur right here, and that minimum looks to be about 1 foot, roughly. This is real data for October 4th and 5th, 2011. Now, for what values do these max and mins occur? It means what inputs. When it says what values, it means what would I have plugged in to get that maximum and that minimum value. Now, this is where my graph is going to start looking like a mess, so maybe I'll delete a couple of my drawings. So I've deleted that, and let's see, it looks about maybe 12:30 in the afternoon. So for the max, the value that occurs at is roughly about 12:30. And the minimum value looks to be about 6 a.m. Now the last part of this is actually asking a very important question. It's extremely important to know when a function is decreasing or when a function is increasing. A function is decreasing when the curve is going down when you read it from left to right. In other words, the outputs are getting lower and lower and lower. So let me highlight where this is decreasing on both of those intervals right there. And if you think about it, decreasing basically means if you were to put a ball, like just a ball, so on it, it would roll to the right. Okay, so you see that in both those cases, a ball placed on that curve would roll to the right. Notice where the decreasing intervals end and where they begin. That's going to be important in our answer. And in fact, maybe I'll even highlight that with a little line here just to show you. Roughly, I'm again very roughly approximating the beginning and the ending of these intervals of decrease. So it looks to me as though our first interval of decrease occurs between about 12:30 and ends at about 1900. So I'm going to say my first interval of increase is between 12:30 and 1900. And notice how I've drawn that interval out. I use open endpoints on it because you normally do not include the endpoints when you're talking about intervals of increase or decrease. It's just because at a point you're not really increasing nor are you decreasing. However, through an interval you can decrease. So from 12:30 to 1900 we're decreasing. And then the second interval, so I'm going to union onto that or glue onto that interval, a second interval. That starts at about, this is about 11 p.m., so that's 2300 hours, and goes on until 6 a.m. It's a very unique function in that your intervals look like they go from big numbers to small numbers, but they don't. It's just that you're going from 11 p.m. to 6 a.m. In that second interval there. And that's how you kind of find out what intervals you're increasing, decreasing on. It's just essentially that you're falling from left to right. Or if you're going to find intervals of increase, you're going to rise from left to right. So in other words, every other interval on that thing that's not highlighted is an interval of increase. Now, some functions are always increasing. Specifically functions involving generally anything with economic data, which is what this is. This is a graph of a per person, in US dollars by the way, a per person per year expenditure for health expenditures in the United States versus Sweden. And you can see that over the years, the United States is an ever increasing graph. In other words, we increase and increase and increase our amount of spending on healthcare per person in the United States every year. Actually, so does Sweden. It's just not as quick of an increase, correct? So if you were to use linear data here, you would find that the slope of the line for the United States is steeper than the slope of the line for Sweden. but linear data would probably not be the best to describe this situation. An additional item I want to note on this previous example is that we can actually talk about the domain and the range of this example. The domain, remember, is a set of all allowable inputs, and in reality, if you're going to talk about this function over all of time, then the domain is any time that exists where Seattle has ocean next to it. So it's pretty much an infinite interval. But just looking at the interval we're given, I could just say, listen, the domain for this given picture goes from about 845, it looks like, and I'll include that as an endpoint. Oh, no, it doesn't go from 845, actually, now I'm looking at it. 11, 10, 9. Yeah, it probably goes from 8, actually. So let me take out the 45 there and just say it starts at 8. And goes all the way up to about 8 a.m., actually. So this will. The weird thing about this graph is that it goes from 8 to 8, but that means 8 the next day. I'm sure that you can understand that. And the range, on the other hand, remember the range is all the set of all possible outputs for the given inputs. The range goes from the minimum to the maximum, and we actually talked about what the minimum and the maximums are. The minimum was 1 foot, the maximum was 11. So it looks to me like the range goes from 1 to 11. From low to high, it goes from 1 to 11. And it hits everything in between. Now, in this next example here, we're going to assume that this is a graph of the function f. So this is f of x here. And the first thing I'm going to state is domain and range. And let's just assume also that this function stops being graphed at these endpoints. That's something you have to assume when you're looking at this function. So let's talk about the domain here. The domain looks to be, and maybe I'll write it over here. Domain, remember, is a set of all possible inputs. It looks to be able to start at about -6, right? That leads to an output. And all of these inputs, all the way up to even a -1, leads to an output. Even all the way up to a +1 leads to an output. And even all the way up to +2 leads to an output, right? Because when I plug in x equals 2, it goes up to a height of 4. It doesn't, remember, when it passes through an open circle, it means it doesn't touch that point. So it goes all the way up to a height of 4. So we can even plug in 4. We can plug in anything beyond 4 all the way up to 6. So that is that the domain goes from -6 to +6, and it looks like it includes those. Had I put an open circle on one of these, I would put a parenthesis on that 6. But there's not an open circle there, so I'm not going to put a parenthesis. The range is a set of all possible outputs. So let's talk about how low this function can go. It looks like it goes all the way down to a height of -4. And it sure does look like that, doesn't it? It goes all the way down to a height of -4. So I'll go ahead and say that the range starts at a height of -4. It climbs. It can reach a height of -2, -1, 0, 1, 2, 3. In fact, let me erase this line here, just so that I can see what I'm doing. 1, 2. It can even reach a height right here of 3. Right? It has a whole bunch of places where it reaches a height of 3. And it goes all the way up to a height of 4, in fact. So the range, again, goes from -4 to 4. Now, if this is an open circle on that end, then the lowest low would not be a bracket. It would be a parenthesis. But that's not the case. We don't have an open circle there, so that's not a worry. Second part of this is asking us to state the intervals of increase. There are several, or at least 2. Intervals of increase, that means when you read it from left to right, I want to know when the graph is climbing. And let me just highlight that for you. It's climbing as I read from left to right. It's climbing in this area here. And then again, in this area here, it's totally climbing, right? But then otherwise, it's not climbing in this region, nor is it climbing in the region in between these blue highlights. So let's talk about what it means. State the intervals of increase. It means what x values lead to all of those y values that are increasing. Well, let's see. It starts at a negative 6, x equals a negative 6, and for all those x values all the way up to x equals negative 1, it's increasing, increasing, increasing. And then all of a sudden we have to skip from negative 1 to 0 because it's falling in that interval. And I'll union onto that starting at 0 and climbing all the way to x equals 2, because for all those x values, again, the function is increasing. And again, I don't include the endpoints for an interval of increase or decrease because technically the function is not increasing at a specific point. It's increasing along an interval. The next part is asking several things. Find f of negative 1. Well, f of negative 1 means go back to negative 1 on the x-axis. What is the possible output for f? In other words, what's the function value at negative 1? Plug in negative 1. It looks to be a positive 1. That's the height. So I'm going to say equals 1. F of 0 is probably the easiest of them all because if you go to x equals 0, the y value looks to be 0. F of 2 means go over to x equals 2 and find out what the output is when you plug in x equals 2. This one I'm going to actually draw that line again just to, again, remind you that it's not going to be 3 here because it passes through that open circle. It goes all the way up to a height of 4. So f of 2 is actually 4. And then the last one's kind of an odd request. What is f of 4.3? And you would think that you wouldn't be able to figure this out, but here's 4.3, roughly right about there, and it leads up to this value here, which is a height of 3. So this is going to be 3. Finally, they're asking what x values, or find the x values so that f of x is equal to 3. That's the same thing as asking what x values can I plug in that will lead to an output of 3. Well, let's look at the output of 3 really quickly. I'll draw a line at the output of 3. It looks to be everything on this line right here. In fact, you can't really see it very well with that in the way, so I'll just have to erase it and show you. It looks like this value and then all the x values that lead to this line. So in other words, for this part right here, I want all the x values starting at 2 and going on to 6, but not including 2. All those x values, anything between 2 and 6, will lead to an output of 3. But also, this x value right here, which looks to be about a 1.6. So I'll include 1.6 with that. Now, one thing you have to know when you have to include just a single point with an interval, when you're going to union those two things together, you're unioning a set of 1 point with a set of a bunch of points. When you only want 1 point, you put it in the brace notation. Not often that you have to do that, but there we have it. Those are all the x values that lead to an output of 3. If I plug in 1.6, it'll lead to an output of 3, or roughly 1.6. And then everything between 2 and 6, not including 2, but including 6. Now, as a recall, I just want you to remember that I did already mention in a previous lecture the vertical line test for determining whether a function, the graph of a function, or a graph actually, represents a function or not. A graph represents a function if any vertical line that you want to place on that graph intersects the graph at most once. And here are a bunch of examples, or at least 3, that illustrate this concept. So this first curve here is a function because every vertical line I tried to graph here hit this curve only once. This second, or actually maybe I should go to C, this third graph is also a function because no matter what vertical line, I shouldn't use green actually, let me use a red. No matter what vertical line I try to draw, it only hits the graph once, at most once. Even through this part right here, because remember That circle means I missed that part of the graph, but I connect up down below. So that would be a function as well. However, this middle curve is not a function because when I draw a vertical line, it hits that curve more than once. So that's just a recall on how to determine whether a graph represents a function or not. It's a very minor skill, but it's a great way to determine whether something's a function visually. Another skill you're going to have when you're trying to graph functions, not only reading graphs and determining domains and ranges and picking off values from graphs, which is actually more important than this skill that I'm about to introduce. You also have to be able to graph objects that you normally don't know what they look like. For example, graphing the square root of 4 minus x. If you're going to do that, building a table is good. It's not really the best technique. We'll learn better techniques later on, but at least is a good start. Now, when I build a table normally, I build a table using x and f of x. However, it's fair game for somebody to write x and y because technically f of x is just a stand-in for the letter y. It doesn't really matter how you do it. Now, let's pick our values for x wisely. If you pick a value like 5, you'll see that 4 minus 5 gives me a negative number underneath the square root, and so that won't work. In fact, I already see I have to pick numbers like 4 or 3 or 2 or 1 or 0, right? Because 4 minus 0 is fine. I could pick a number like, I don't know, negative 1, negative 2, negative 3, negative 4. Now that's a silly amount of points in reality. Those points it's just a ridiculous number of them. But it's good enough that we can go ahead and try this out. When x is 4, I see I have the square root of 4 minus 4, or in other words, the square root of 0, which is actually 0. When x is 3, I get the square root of 4 minus 3, which is the square root of 1, which is 1. When x is 2, I get the square root of 4 minus 2, which is actually the square root of 2. When x is 1, I get the square root of 3. When x is 0, I get the square root of 4 minus 0, which is 2. When I plug in a negative 1, I get the square root of 4 minus a negative 1, or in other words, 4 plus 1, square root of 5. And square root of 6, square root of 7, and the famous square root of 8, which actually can reduce down to 2 square root 2. And what I'll do is I'll use these points, at least some of them, to help me plot this curve. But I said some of them because in reality, some of those points right there are radicals, and I just don't like to deal with radicals. So I create my axes. I'll go over 1, 2, 3, 4, and this will be my point 4, 0. I'll put that in red. And then 3, 1. Let me go ahead 1 on my x-axis here. 3, 1 is right here. And then the next most convenient one is 0, 2. So let me go ahead and plot that as well. And 3 points generally do not make a beautiful function. You might have to plot a few other points. If you do, I'll just go ahead and plot negative 4 just to kind of get a better view of this. So negative 1, negative 2, negative 3, and negative 4. When you plug in negative 4, remember it came out as the square root of 8, or in other words, square root of 2 times 2, which is 2.8 roughly, very roughly. So this will be at a height of 2 and a little bit more. Let me just go ahead and put that above here. Something like this. So it looks as though I have a curve that does something like this. I'm not going to get it too accurately because I'm free drawing this thing. I get a curve like this that seems to go off forever in the backwards direction. Now from here, I should be able to state the domain and range just kind of by eyeballing it. The domain on this seems to start, in other words, the set of x values that I can plug in, seems to be any negative number that I want. You can plug in like a negative billion, right? 4 minus a negative billion is 4 plus billion, or in other words, a billion and 4, and you could take the square root of that. So it looks to me as though the lowest I can plug in is negative infinity. And then the largest x value I can plug in is that positive 4. And I can actually plug that in, so I'll put a bracket on that. The range, on the other hand, and this usually is only able to be found by graphing it, honestly. The range, the lowest output or lowest y value that this can have is y equals 0, and it can actually be 0 because we see it right here. And it'll keep climbing as time goes on. In fact, if you think about that billion comment, if you plug in a huge number like, I don't know, 10 to the 10th power, okay, that's a huge number. That's equal to the square root of, I'm sorry, a negative 10 to the 10th power. That's equal to the square root of 4 minus a negative 10 to the 10th power, which is basically the square root of 4 plus 10 raised to the 10th power. And if you do that, that's actually going to come out to be roughly 100,000. So no matter what, I can always keep this graph growing. I just have to plug in larger and larger negative values. So the range on this will keep climbing all the way up to infinity. Hard to tell that, though, to be honest with you, just by looking at this graph. And that's something to be very wary of when you graph functions by building tables of values. It's one of the weakest methods to graph a function, first of all. And then secondly, you can't really always get the entire graph of a function just from a table of values. Often it's, like I said, the weakest method. Final thing I want to mention in this lecture is the types of functions you can expect. It turns out that everything we've kind of dealt with so far in mathematics has been basically functions. You have things that used to be called linear equations, and you would graph a linear equation. Now those are called linear functions. So we have linear functions, and generally they're of the form, instead of y equals mx plus b, they're f of x equals mx plus b. But there really is no other change in a linear function. In other words, there's nothing new to it. You have a slope and an intercept. You can graph them, right? We also have the next power up, which is the quadratic functions. So we had quadratic equations in the past. Now we have the quadratic function, which is essentially f of x equals, instead of y equals, it's f of x equals ax squared plus bx plus c. And there's all different kinds beyond there. There are cubic functions. That's stuff with, instead of x squared, it's with an x cubed. So let me write that one out. You have absolute value functions. And then there's all different kinds of functions. But most of these actually we've seen in the past. But still, if you're asked to graph any of these, if you're asked to graph a linear function, use the slope and the y-intercept. If you're asked to graph a quadratic function, use the methods that I've given in previous lectures to graph quadratics. If you're asked to graph a cubic function, your best bet is to create a table of values for now. We might be able to create some good methods later on, but for now you're going to have to create a table of values. And any other type of function you're given, you can generally just create a table of values to graph them. And offhand, I'm trying to think of what else I can really mention about graphs of functions. There's not much else I can mention. There's a lot of little sub things that you might get. There's hundreds, if not thousands, of problems out there. And so a single lecture can't cover every single problem. And you don't want to do that anyway. The idea behind learning mathematics is to give yourself the tools and to understand the tools well enough to then go and use those in any type of problem or application where the tool will apply. So to give examples upon examples is probably not the best idea here.